Gaseous diffusion, Wikipedia audio. Gaseous diffusion is a technology used to produce enriched uranium by forcing gaseous uranium hexafluoride through semi-permeable membranes. This produces a slight separation between the molecules containing uranium-235 and uranium-238. By use of a large cascade of many stages, high separations can be achieved. It was the first process to be developed that was capable of producing enriched uranium in industrially useful quantities. Gaseous diffusion was devised by Francis Simon and Nicholas Curti at the Clarendon Laboratory in 1940, tasked by the Maud Committee with finding a method for separating uranium-235 from uranium-238 in order to produce a bomb for the British Tube Alloys project. The prototype gaseous diffusion equipment itself was manufactured by Metropolitan Vickers at Trafford Park, Manchester, at a cost of £150,000 for 4 units. This work was later transferred to the United States when the Tube Alloys project became subsumed by the later Manhattan Project. Of the 33 known radioactive primordial nuclides, 2 are isotopes of uranium. These 2 isotopes are similar in many ways, except that only 235U is fissile. In fact, 235U is the only naturally occurring fissile nucleus. Because natural uranium is only about 0.72% 235U by mass, it must be enriched to a concentration of 25% to be able to support a continuous nuclear chain reaction when normal water is used as the moderator. The product of this enrichment process is called enriched uranium. Background: gaseous diffusion is based on Graham's law, which states that the rate of a fusion of a gas is inversely proportional to the square root of its molecular mass. For example, in a box with a semi-permeable membrane containing a mixture of 2 gases, the lighter molecules will pass out of the container more rapidly than the heavier molecules. The gas leaving the container is somewhat enriched in the lighter molecules, while the residual gas is somewhat depleted. A single container wherein the enrichment process takes place through gaseous diffusion is called a diffuser. UF6 is the only compound of uranium sufficiently volatile to be used in the gaseous diffusion process. Fortunately, fluorine consists of only a single isotope 19F, so that the 1% difference in molecular weights between 235 UF6 and 238 UF6 is due only to the difference in weights of the uranium isotopes. For these reasons, UF6 is the only choice as a feedstock for the gaseous diffusion process. UF6, a solid at room temperature, sublimes at 56.5 degrees Celsius at 1 atmosphere. The triple point is at 64.05 degrees Celsius and 1.5 bar. Applying Graham's law to uranium hexafluoride. Where? This explains the 0.4% difference in the average velocities of 235 UF6 molecules over that of 238 UF6 molecules. UF6 is a highly corrosive substance. It is an oxidant and a Lewis acid which is able to bind to fluoride. For instance, the reaction of copper fluoride with uranium hexafluoride in acetonitrile is reported to form copper heptafluorouranate, Cu2. It reacts with water to form a solid compound, and is very difficult to handle on an industrial scale. As a consequence, internal gaseous pathways must be fabricated from austenitic stainless steel and other heat-stabilized metals. Non-reactive fluoropolymers such as Teflon must be applied as a coating to all valves and seals in the system. Gaseous diffusion plants typically use aggregate barriers constructed of sintered nickel or aluminum, with a pore size of 10-25 nanometers. They may also use film-type barriers, which are made by boring pores through an initially non-porous medium. One way this can be done is by removing one constituent in an alloy, for instance using hydrogen chloride to remove the zinc from silver zinc. Because the molecular weights of 235 UF6 and 238 UF6 are nearly equal, very little separation of the 235U and 238U is affected by a single pass through a barrier, that is, in one diffuser. It is therefore necessary to connect a great many diffusers together in a sequence of stages, using the outputs of the preceding stage as the inputs for the next stage. Such a sequence of stages is called a cascade. In practice, diffusion cascades require thousands of stages, depending on the desired level of enrichment. All components of a diffusion plant must be maintained at an appropriate temperature and pressure to assure that the UF6 remains in the gaseous phase. The gas must be compressed at each stage to make up for a loss in pressure across the diffuser. This leads to compression heating of the gas, which then must be cooled before entering the diffuser. The requirements for pumping and cooling make diffusion plants enormous consumers of electric power. Because of this, gaseous diffusion is the most expensive method currently used for producing enriched uranium. Scientists working on the Manhattan Project in Oak Ridge, Tennessee, developed several different methods for the separation of isotopes of uranium. 3 of these methods were used sequentially at 3 different plants in Oak Ridge to produce the 235U for Little Boy and other early nuclear weapons. In the first step, the S-50 uranium enrichment facility used the thermal diffusion process to enrich the uranium from 0.7% up to nearly 2% 235U. This product was then fed into the gaseous diffusion process at the K25 plant, the product of which was around 23% 235U. Finally, this material was fed into calutrons at the Y12. These machines employed electromagnetic isotope separation to boost the final 235U concentration to about 84%. Technology. The preparation of UF6 feedstock for the K25 gaseous diffusion plant was the first ever application for commercially produced fluorine, and significant obstacles were encountered in the handling of both fluorine and UF6. For example, before the K25 gaseous diffusion plant could be built, it was first necessary to develop non-reactive chemical compounds that could be used as coatings, lubricants, and gaskets for the surfaces that would come into contact with the UF6 gas. Scientists of the Manhattan Project recruited William T. Miller, a professor of organic chemistry at Cornell University, to synthesize and develop such materials, because of his expertise in organofluorine chemistry. Miller and his team developed several novel non-reactive chlorofluorocarbon polymers that were used in this application. Calutrons were inefficient and expensive to build and operate. As soon as the engineering obstacles posed by the gaseous diffusion process had been overcome and the gaseous diffusion cascades began operating at Oak Ridge in 1945, all of the calutrons were shut down. The gaseous diffusion technique then became the preferred technique for producing enriched uranium. At the time of their construction in the early 1940s, the gaseous diffusion plants were some of the largest buildings ever constructed. Large gaseous diffusion plants were constructed by the United States, the Soviet Union, the United Kingdom, France, and China. Most of these have now closed or are expected to close, unable to compete economically with newer enrichment techniques. However, some of the technology used in pumps and membranes still remains top secret, and some of the materials that were used remain subject to export controls, as a part of the continuing effort to control nuclear proliferation. In 2008, gaseous diffusion plants in the United States and France still generated 33% of the world's enriched uranium. However, the French plant definitively closed in May 2012, and the Paducah Gaseous Diffusion Plant in Kentucky, operated by the United States Enrichment Corporation, ceased enrichment in 2013. The only other such facility in the United States, the Portsmouth Gaseous Diffusion Plant in Ohio, ceased enrichment activities in 2001. Since 2010, the Ohio site is now used mainly by Areva, a French conglomerate, for the conversion of depleted UF6 to uranium oxide. As existing gaseous diffusion plants became obsolete, they were replaced by second-generation gas centrifuge technology, which requires far less electric power to produce equivalent amounts of separated uranium. Areva replaced its Georges Besse gaseous diffusion plant with the Georges Besse II centrifuge plant. History. Current status.